So hi guys, last class we have seen all the lessons, all the four formulas on arrangements. So before we move on to questions on arrangements in this lesson, I first also want to tell you about the questions on distribution of distinct objects, which is used, which gets solved using the MLP rule. And the first question on that, there are three standard questions on that. The first of which is, in how many ways can you send 5 letters if you have 4 servants? 5 letters if you have 4 servants, and any servant can be used any number of times. So in this scenario, if you visualize the solution, the solution here is that you have to send letter 1 and send letter 2 and send letter 3 and send letter 4 and send letter 5, and for each of these 5 distributions you have 4 ways of sending it, because you have 4 servants, so any of the 4 servants can go every time. So the correct answer to this question becomes 4:5. There is a parallel question which talks about what is the number of ways in which you can wear 6 distinct rings on 4 fingers, if any finger can have any number of rings. So again, the choices in this case, again you can think about this through MNP, that your first objective is to wear ring 1, and your second objective is to wear ring 2, and your third objective is to wear ring 3, and each objective can be fulfilled in 4 ways, because every ring can go on to 4 fingers. So going that way, when you wear the 6th ring, your answer would be 4:6. So these kind of questions, there's always a confusion about whether it's 6:4 or 4:6. Same case here. Do you use 5:4 or 4:5? So let's say you have 8 servants and 5 letters. Let's say you have 3 fingers and 4 rings. What do you use? So you automatically know that the answer is either 5:8 or 8:5. In this case, the answer is either 4:3 or 3:4. But which one to use? One way to resolve it, to go through all the MNP rule and defining what the objective is and what the distribution is. But a much better way to define this is that if you look at servants and letters, between these two, one of them is repeatable. You can repeat one of them, and the other is not repeatable. You cannot repeat the second. So if you look at if you think about servants and letters, you can send a servant again and again, but you can't send the letter again and again. So the repeatable aspect is servants, and the not repeatable aspect is letters. Likewise, in fingers and rings, you're wearing 4 rings in 3 fingers. In fingers and rings, again you'll be wearing a ring only once. You can repeat a finger, you can wear a ring on the same finger, you can wear 2 rings on the same finger. So in this case, fingers are repeatable and rings are not repeatable. And in all these cases, the answer will always be repeatable to what is not repeatable. So in the servant's letter case, the answer will be 8:5, because 8 is the repeatable number. And the fingers and ring case, the fingers were repeatable, so the answer will be 3:4. So just remember it this way, and you'll never fail to see what is repeatable and what is not repeatable in this situation, and hence you'll always get an answer to this immediately. And this is the resolution of the confusion, that should we do 4:3 or 3:4, right? So this is one part of this, and then of course we move to the standard questions on arrangements. So arrangements questions, when you talk about them, they have you have generic questions like the one we just did, that or some simple questions like I want to make A, B, C, D, E, F sit in 3 places. So the answer will be 6 into 5 into 4. This can be done using a 6p3, but as I've mentioned to you earlier, try to avoid it, right? A team of 16 players, and you will see more reasons for avoiding using NPR as I'll show you now. From a team of 16 players, you're making a batting order of 11. You're making a batting order of 11. So in this scenario, since you're making a batting order of 11, there are two ways to do it. In fact, three ways to do it. First place can be filled in 16 ways, the second way in 15 ways, the third in 14 ways, all the way to the last in 6 ways. One way to do it might seem cumbersome, so you have an alternative. Select 11 players and arrange them NCR into R factorial, or of course you have the 16p11 route also here. So all three work here, but this might be the best way to do it, and most of the times you might have an answer either in this form or that form. So you should recognize that this form and this value are the same. So if you get this, you should be able to visualize that it's that, right? So you can do these questions. Of course, both these questions can be done using NPR also, but you really don't need NPR as you can see in these two questions. So but the moment you twist the question, suppose I give you this question that there are 16 players in a cricket team and I want to form a batting order of 11 such that the captain is always selected. Now this is where NPR fails, because you can't do this any longer using NPR. The captain is always selected. You can no longer do this using NPR because in this scenario, there's no way NPR will work. NPR is a situation where you have 16 players, you want to select 11 and place them in a circle, or you place them on a line. In this scenario, there's a twist in the selection. So in such cases, NPR stops working, and the only way to do things is to select separately and arrange. The arrangement in such scenarios should be done using R factorial. Keep your selection separate and keep your arrangement separate. You'll use R factorial to arrange if what you are selecting is all distinct. But if what you are selecting has identical objects also, then you will use the R factorial modified to arrange. So let me show you examples of that. But before that, let's finish this question. So in this scenario, if I think of the selection, we have already done this question as a selection question in one of the previous lessons in this chapter. The selection here is 15C10. The number of selections possible here is 15C10. And will always mean a multiplication, and 15C10 ends up selecting 11 people for you because this is the case of pre-selection of the captain. So 15C10, and now I have to arrange these 11 people in 11 places. So 15C10 into 11 factorial becomes the correct answer to this question. And as you saw, you have to anyway bypass NPR usage. So the first sign of difficulty in a question in arrangements, NPR will stop working. So there's absolutely no point continuing using NPR. Your NCR into R factorial logic or the 9th, 10th and 11th formulas together will suffice to do all questions on arrangements for you. So if I go back to more questions, let's say there's this group of questions where we talk about 7 people, A, B, C, D, E, F, G, need to be placed on 7 places. In how many ways can they be arranged? So the answer is 7 factorial, right? And then there's modifications to this question. In how many ways can they be arranged if A and B are together? If A and B are together, in that case, the arrangement scenario is seen as AB as one person and 5 more people separately. So AB as one person and 5 more people separately. So effectively, you have 6 people whom you are arranging, because AB is taken as one person. So 6 people in 6 places will be 6 factorial. But that is not the answer completely, because you also have to, there has to be an AND also account for the rearrangement of AB amongst themselves. So you can multiply the 6 factorial by 2 factorial to get the answer in this situation when you're talking about A and B are together, right? So if I tell you that A, B, C are together, 7 people, 7 places, such that A, B, C are together, the solution will be, you keep A, B, C as one person, so you effectively have 5 people in 5 places, which would be 5 factorial, and the internal arrangement of A, B, C, which is 3 factorial, and because it's connected to the AND, we have to multiply the two numbers to get you this answer, right? Then A, B, C, D, E, F, G on a straight line such that A is always in the middle. These are the variants to this question, such that A is always in the middle. A, B, C, D, E, F, G in a straight line such that A is always in the middle will mean that A is fixed, and effectively what you have is 6 people, 6 places, and that would be 6 factorial. And as you can see, all these questions you're doing through the R factorial tool without the R factorial formula, without the need for NPR at all, right? Let's look at one more case. A, B, C, D, E, F, G, such that A, B, C, D, E, F, G arranged in 7 places on a straight line, such that A and B are not together. A and B are not together. So in this scenario, what you do is you can do this with all arrangements minus arrangements with AB together. So in this question, the answer would be 7 factorial, because that's all the arrangements of A, B, C, D, E, F, G. I meant all arrangements here, not all A. And similarly, minus arrangements with AB together, and that is, we know that if I take AB as one person, then this is 6 factorial into 2 factorial, because I'll have C, D, E, F, G, 7 people, effectively 6 people, so 6 factorial into 2 factorial. So if I subtract all arrangements minus arrangements where AB are together, I'll get the number of arrangements with AB not together. So this is the next question on this. And one last question on this is, if I tell you that A is, let's say, if I change this to no 2 of ABC are together. You want to place A, B, C, D, E, F, G on a straight line so that no 2 of ABC are together. So in this scenario, you can't do this with all arrangements minus arrangements of ABC together, because in this scenario, an arrangement of this nature is also not to be counted, because in this case AB are together and the question says no 2 of ABC are together. So in this scenario, the approach can be in this form. So if you visualize the 7 places as places 1, 2, 3, 4, 5, 6 and 7, so what you can do in this scenario is you can decide the places for ABC. So if you decide places 1, 3, 5, then automatically you know that there will be no interference between 2 of A, B, C sitting together. So first you define all the possibilities of 3 people sitting so that they are not together. So in this case, if you go systematically, this is the seats you will see: 135, 136, 137. Now once you have finished 137, then you change to 146, and 147. Don't do that before you finished with 1-3s. Now at this point 1-4s are finished. Then you move to 1-5. And 1-5-7 is a case of arranging, of putting ABC not where no two of them are together. And at this point there's nothing else with 1 because you can't go to 1-6. So that then takes me to 2. So if I start with 2, I can have a 2-4-6 or a 2-4-7. And then I can have a 2-5-7. And last but not least, I can have a 3-5-7. So each of these are going to be symmetrical. There are 10 solutions here, and each of this will have the same answer. And that's how you add speed to your solving. Don't try to add speed by breaking this faster because you'll make mistakes. So whenever the questions get broken down into parts, follow the breakdown and then do or add speed by doing symmetry, by using symmetry, or by using the same solution for all of them. So for example, in this case, if I'm thinking of 3-5-7 being ABC in whatever order, so that means I have to place ABC in these 3 places. So ABC in 3 places is 3 factorial, and D, E, F, G have to go in the other 4 places. So DFG in 4 places will be 4 factorial. So 3 factorial into 4 factorial becomes the answer, and hence this would become the right question or the right solution to this. So this is a gamut of questions which can be described as situation based arrangement questions, and there's an assignment at the end of this which you will find more questions on this in the next lesson. And I've also done the distributions in this lesson, so I'm sure you are now comfortable with distribution of distinct objects. Remember the repeatable to the not repeatable logic there. All questions on that will work that way. And in the next lesson we'll move into arrangements based on words based on word formation. So there's a whole set of questions based on words being formed. So we'll come to those in the next lesson. And then that will follow with the numbers, and that would close this chapter with a small lesson on circular arrangements, which is 2-3% of this chapter, which you should just know the formula for. So I'll see you on the other side. Goodbye for now, and please do the assignment that is attached to this. Bye bye.